Hello guys, I hope you are doing good. Welcome back to another session of mold design using SolidWorks. In this session, we will mainly be focusing on parting surfaces. I will explain what parting surfaces are, the various types of parting surfaces, and we will also look at some example cases and understand the selection of parting surfaces. And after that, we will also cover the concepts of matching draft, shrinkage, and core cavity inserts. So first, we will start by understanding what a parting surface is. In the second session, I had given you a brief explanation of what a parting line is. I had mentioned that the parting line is the line that splits the mold into two parts, that is the core and the cavity. The concept of parting surface is the same as that of parting line. The parting surface is the surface that splits the mold block into two parts, the core and the cavity. I will elaborate on this point a little by using the model which I created. So let's take this simple model for understanding where exactly does the parting surface lie in the mold. This model which you see is hollow, as you can see in the image on the right. So let's say I want to create a mold for making this part. So I will first select a parting line for the mold. In the figure you can see the parting line is indicated by the blue line. Now according to the location of the parting line, a parting surface will be formed. In the diagram, the blue surface is the parting surface for the mold. So this is the surface where the core and the cavity for the model will meet. The portion of the mold block above the light blue surface will form the cavity, and the portion of the mold block below the blue surface will form the core. Here I have an image showing the core and the cavity for the part, and during the injection molding process, these two blocks will come into contact with each other. So the surface where these two blocks are touching each other, which is displayed by the highlighted blue surface, is the parting surface for the mold. So in the previous slide, what we saw is called the flat parting surface. But all the parting surfaces are not similar. Based on the different contours or profile of the part, the shape of the parting surface changes, and it has been classified into four different types: the flat or straight parting surface, stepped parting surface, angled parting surface, and the profiled parting surface. I will be explaining each type in the further slides. So here we have a part that will have a flat parting surface. On the right you can see the core and the cavity for the part, and the green line indicates the parting surface where the core and the cavity blocks will meet. So whenever you have this type of flat surface, it is called a flat or a straight parting surface. Machining of this kind of surface is the easiest, and that is why flat parting surfaces are preferred over other types of parting surface. But it is not always possible to provide a flat parting surface, as we will see in the further slides. Here we have a model similar to the previous one, but in this case the base of the model is not in the same plane. So we can't have a flat parting surface in this case. On the right, you can see what the core and the cavity will look like for this model. The green line again indicates the parting surface for the model, and you will notice that though the parting surface is still flat, but it is located in two separate planes. So this type of parting surface is called the stepped parting surface. Now here we again have a similar component, but this time the base of the component is at some angle. So again we can't have a flat horizontal parting surface for this part, and the core cavity mold blocks will be at some angle, as you can see in the image. But the thing to note here is that even if we have an angled parting surface, the entire mold block won't be created at an angle as shown in the image. Instead of that, as you can see in the bottom image, the inclined profile of the component will be followed only up to some distance, which is usually somewhere around 20 to 30 mm, and then the blocks are made flat again. This is done because, as I mentioned earlier, machining is easier if we have a flat horizontal surface. And once the profile of the component is captured in the mold block, there is no further point in continuing the same angled surface. Even if you have the complete mold block at some angle, or if you have the mold block at some angle close to the component and then a flat profile, the end result as far the molding of the component is considered will still be the same. This addition of flat surface instead of angled surface is done only to allow easier machining. And another point is, if in actual practice we were creating a mold for this component, then we would be providing some relief in the highlighted region. So that basically means that the core and cavity blocks won't come into contact in this region. Now this is done in order to avoid the rubbing of the core and cavity blocks. In the rest of the parting surface, the core and the cavity blocks do come into contact, but as the core is moving away from the cavity, the blocks get instantly separated and there is no rubbing of the mold blocks. But in the highlighted region, the surface is at a 90-degree angle. So here, as the core block moves away from the cavity, it will rub the cavity block, and over time it will damage the mold blocks. In general, we try to avoid steel-to-steel rubbing in mold blocks, so that is why a relief is provided to avoid damage to the blocks. And here we have a part that would require a profile parting surface. You can see the base of the part has a curvature, and if we want the molded component to have a curved base, then you have to create a curved mold block for that. So whenever you have a curved profile like this case, we will have to create a curved or a profile parting surface. And as I mentioned previously, we don't need to make the entire mold block with a curved profile. We will have the curved profile close to the component, and after that we can have a straight parting surface as shown in the figure for easier machining. Now we will be looking at some example cases and understand the selection of parting surfaces for these parts. Since the parting surface defines the mold blocks for a mold, selection of parting surface will also affect the difficulty in creating the mold for the part. I will explain this point using the hexagonal component which you see on the top right. So the blue part which you see is the component to be manufactured. And on the left and the right, you can see two different parting surfaces for this model. In the left case, you can see that once the component is molded, the core can easily move to the left and the part can come along with the core. But in the right case, due to the selection of the parting surface as shown in the figure, the part cannot move along with the core. It will get stuck in the cavity. This is because due to the selection of the parting surface on the end, an undercut has been formed in the second case, which is denoted by the red color. So here you can see how the selection of parting surface can increase or decrease the difficulty of demolding process. The selection of parting surface should be such that a minimum number of undercuts are formed and the demolding process is also simple. For this specific model, the selection of the parting surface as shown in the left diagram is more preferable. Now here we have a case showing where the angled parting surface would be more preferable. You can see the example component on the top right. First, let's have a look on the left case where a straight parting surface was used. Here the blue colored part is the component and the green color indicates the parting surface. In this case, the parting surface was selected along the flat base of the component. But once the material is injected and solidified, if we try to remove the part from the mold, it won't be possible due to undercuts, which is indicated by the red color. Now let's look at the second case. In the second case, an angled parting surface is selected instead of a straight parting surface. And you can see that due to this selection, there are no undercuts present in the model now, and it can be easily ejected from the mold. Since the machining of straight parting surfaces is easier, if possible we try to avoid other types of parting surface and always go for the straight parting surface. But in this case, use of angled parting surface helps us in avoiding undercuts which cannot be achieved using the straight parting surface. So for this specific model, use of angled parting surface is the preferred method for designing the mold. Here we have another example where we will have to use the profile parting surface. As the base of the spoon is not along a single plane, we will have to use a parting surface that is along the profile of the spoon. If you take any plastic spoon, you will notice a parting line along the spoon profile as you can see in the image. And the red lines which you see indicates the inlet for material injection into the mold. Here we have another example where angled parting surface will be used. In this case, let's assume the material injection to happen along the path shown in the red. In this case, what will happen is, as the injection pressure of the molten plastic is very high, it will push the upper cavity block towards the left, and if that happens, the part dimensions won't be accurate. So in cases like this, a similar angle profile in the opposite direction would be made on the block to lock the core cavity blocks as shown in the diagram. So this locking issue would only happen if we are molding only one component. If we were molding two components together, then the mold block would look something like this. So here we don't have to worry about the blocks moving in the horizontal direction. The inlet of the molten material will happen from the center, which is shown in red in the diagram, and the forces on both the sides will be balanced. Now let's have a look at another example. Let's say I want to create a mold for the part which you see here. So here there are two images showing two different parting surfaces. In both the cases we have a flat parting surface, and in both the cases there won't be any undercuts in the model. So as far the ease of demolding and machining is concerned, there is no difference between the two parting surfaces. But in case 1, the selection of the parting surface is such that it will leave a mark on the model as you can see in the image. So in this case, parting surface on the right side will be preferred just because there won't be a visible parting line in the final model. The selection of the parting surface between these two cases is made purely on aesthetic basis. Now I would like to explain the concept of matching draft. to explain this concept, I will be using a model which you can see here. And I have also created another model with a slight modification which you see here. The difference between the two models is that the left one has a 90-degree cut in the groove, whereas in the second one, there is a small inclination as you can see in the image. And I have also created the core and the cavity blocks for the model, and you can also see the assembled mold block for the model. So here let's focus on the side view of the mold block for both the blocks. In the left case, where we have a 90-degree cut groove, when the core block tries to move in the downwards direction after the plastic material is solidified, the core steel block will rub against the steel cavity block as you can see in the animation. So when this process takes place repeatedly, the core cavity blocks will get damaged, and once the blocks are damaged, the plastic material will seep through the cracks in the mold blocks, resulting in flashes. Flashes is the defect where the extra material is formed along with the component. But in the right case, since the cut is inclined, there won't be any rubbing of the core blocks. When the core block moves downwards, it will immediately get separated from the cavity block. Now, this concept is similar to the concept of drafts for plastic parts that I had explained previously. But here we are talking about the steel mold blocks and not the plastic part. For plastic parts, I had mentioned that there should be at least 1/4 to half a degree of draft. That point was for plastic to steel contact. The concept of matching drafts is for steel to steel contact. The rubbing of core and cavity blocks is an even bigger issue, and the rubbing of core cavity blocks won't happen in all of the models. But in the models where it does occur, like the model which we are discussing, we need to have at least 7 degrees of inclination so that the steel blocks don't rub against each other. So let's go back to the previous model with the 90-degree cut. So if you get a part like this for mold design, you should notice that there is a side groove in the model which has a 90-degree cut. This would in turn mean that if we try to make a mold for this block, then the mold blocks will get damaged over time. So as a mold designer, you are supposed to tell the product design team or the customer that there are no adequate matching drafts in the given model and a revision of design is required. You can also suggest that an inclination of 7 degrees can be added to make the diagram look like the second image. And once you receive the product with adequate matching draft, you can proceed with the mold design. Now there is another thing that I would like to explain here. While explaining the angled parting surface, I had mentioned that we don't follow the profile of the component throughout the entire mold block to ensure easier machining. Similarly, in this case too, we won't follow the groove profile throughout the mold block as you can see in the diagram here. The image may appear glitched, but it's not. It's directly taken from SolidWorks. This is how overlapping surfaces look in SolidWorks. In this case too, similar to the angled parting surface, we will follow the profile of the component till some distance, usually 25 to 30 mm, and then we will make it as a flat parting surface as you can see in the diagram. And in this case too, we will be providing a relief where the core and the cavity blocks have a 90-degree profile as you can see in the sectional view of the mold block. The relief is provided so the core block does not rub with the cavity block when it moves in the downward direction. Now let's look at the concept of shrinkage. I had explained the concept of shrinkage in brief during the DFM session, but here I will be elaborating on the same topic. For explaining the shrinkage, I will be using the same model which I had used for explaining the straight parting surface. Let's say you're given this model with all the dimensions and you're assigned the task of creating a mold for it. Now, if you create mold blocks for the same dimension as shown in the figure, then once the molten plastic material gets solidified, the component will shrink and the final part which you obtain will be even lesser in size compared to what you see in the diagram. In order to avoid this problem, we always create a mold for a model size bigger than what is actually desired, as you can see in the image. Now, you might wonder how we will know the exact increment in size of the mold to account for the shrinkage. For that, as a mold designer, you will always get information regarding the material that will be injected in the mold and the shrinkage value for that material. Shrinkage value is a material property and the value of shrinkage is always fixed for a specific material. For example, let's say the product design team has mentioned that the plastic material they are using for the component has a shrinkage value of 0.5%. So in order to account for the shrinkage of the component in the mold, you will have to create a mold for a component that is 0.5% bigger than the desired component. In the right diagram which I have created, all the dimensions are 0.5% bigger than the desired dimensions what you see on the left. If you want to confirm the values on the right, then you can convert the percentage value into fraction by dividing 100 and then add the value of 1 to get the factor by which you need to increase the value. So for 0.5% shrinkage, you will divide 0.5 by 100 and you will get 0.005. Add 1 to it, the value becomes 1.005. So 1.005 is the scale factor, and all the values which you see on the right is the product of the original dimensions and 1.005. Now I will be explaining the concept of core and cavity inserts. Here again I am going to use the same component to explain the concept. First, I would like you to focus on the left diagram. Here we have a normal core and the cavity, as we have seen multiple times throughout this course. But the thing to notice here is that the entire core and the entire cavity block is formed using a single material. When the core and the cavity profiles are cut in a single large block, it is known as an integral core and cavity block. Now let's look at the second case. Here, 2 blocks are used on the core side and 2 blocks on the cavity side. There is a smaller red and green color block which has the profile of the part, and then there are large grey flat blocks around it. So here the core and cavity blocks are not made up of a single integral block. The grey part is a separate block and the red block is inserted into the grey block so that the 2 blocks together function as the complete core block. So as far the functioning of the core and the cavity is considered, both the integral and the core cavity insert mold blocks produce the same results. So why do we need the insert blocks separately? That's because as we keep creating plastic components in the mold, over time the blocks may wear out or get damaged. So in the first case where we use the integral block, the entire core and cavity block will have to be replaced when the mold blocks wear out. But in the second case, once the core and cavity insert gets worn out, only the insert will be replaced by another insert instead of replacing the entire block. This helps in reducing the overall cost of injection molding. In actual practice, the inserts are made using high-grade steel and the remaining blocks are made using lower-grade steel to further reduce the cost of the mold. Now these inserts are only used in the final mold, which is used in the actual production process. When we are designing the mold for the first time, that design is only for creating prototype products, and anyways high-grade steels are not used for creating molds for prototype products. So during the initial design of the mold, you don't need to create these inserts taking cost reduction into account. So in the SolidWorks session 2, I probably won't be creating these inserts. We might create inserts in some cases, but that won't be for the reason of reducing the cost. It will be for a different reason, and I will explain that in SolidWorks session itself. So in this session, we covered the parting surface. We looked at various types of parting surfaces, and we also saw some example cases to understand the selection of the parting surface. After that, we also learnt about matching drafts, shrinkage, and core cavity inserts. And that's it for this session. Thank you for watching the video.